Hello, it's Victor, and this is a solution for the CodeForces problem 1406A.
This is an easy division 2 problem and is an implementation problem based on some observations. Now, let's take a moment and read the problem statement yourself and make some early guesses. The problem is stated as follows. You are given a set of non-negative integer numbers and a max function. A max function on a set is the smallest non-negative integer that is not contained in the set. For example, for a set of numbers 0, 1, 2, 3, the max function equals 4. For a set of 0, 1, 2, 4, 8, the max function equals 3. For a set of 1, 2, 3, the max function equals 0, and so on. For an empty set, the max function equals 0 as well. So you are given the source set of numbers, and you have to split the source set in two sets somehow, so that if you add the max function of the first set and the max function of the second set, you get the maximum possible result. Return the value of this result. Let's introduce some examples. For a source set of 0, 2, 1, 5, 0, 1, one of the optimal splits would be 0, 1, 2, with the max function value of 3, and 0, 1, 5, with the max function value is 2. So the answer is 5. For a set of 0, 1, 2, the optimal split is 0, 1, 2, and an empty set. For this operation, the answer would be the max function of the first subset, which is 3. You can find more examples in the original problem statement. Now, please take a pause again and try to think of possible solutions or make some observations. Okay, let's start with some observations here. First, the max calculation could be presented as an iterative process. It will function roughly as follows. Does the set contain 0? If not, then the max value is 0. Otherwise, we ask a question. Does the set contain 1? If not, then the max function value is 1. Otherwise, we ask a question. Does the set contain 2? If not, then the max value is 2. Otherwise, we ask a question. Does the set contain 3? If not, then the max value is 3. Otherwise, we ask a question, and so on. This calculation is naive, and it should be enough for simple cases. Second, adding a new element to a set cannot decrease its max function. You can pause the video and think why. The answer is when we calculate a max number using our algorithm, adding a new element can only turn one of the steps from no to yes, and we can only move further. Let's analyze the source set iteratively in the same way, but now we will pay attention to how many times every number presents in the set. Let's go. If 0 is not in the source set, we could add it to none of the target sets, and the max values of the target sets would always be zeros, no matter how we split the source set. If 0 is in the source set and there is only one 0 in it, we can add it only to one set. The max value of the subset without 0 will always be 0, and we will not be able to change it. As we cannot change it, it is optimal to store all the remaining numbers in the subset that contains 0. The answer to the problem will be the max value of the full set. If there are two zeros, it is optimal to put them into two subsets. In that case, the max values of both subsets will be greater than 0. At least one for each, and we will move next. Now let's consider ones. If there are no ones, the max values of both subsets will equal 1, and the answer would be 1 plus 1 equals 2. If there is only one 1 in the source set, we can add it to any subset. As the subsets are equal from our point of view, we select any. Now one subset contains 0, 1, and the other contains only 0. As we don't have ones anymore, from now on the max value of the second subset would be always 1, because we don't have another 1 in the source set to add there. and we can safely add all of the remaining elements to the first set. The answer is the max value of the first set plus 1. If there are more than 2 ones, we should put them in both of our subsets. In that case, the max values for both subsets will be
no less than 2.
As you see, we have a process similar to a naive max search. One extra thing worth adding is we can maintain the subsets as well as check the inclusion into the source set using a map with logarithmic complexity per operation, or an unordered map with an expected constant time complexity per operation. Because the numbers are in a range of 0 to 100, we can follow the algorithm in its implementation directly. If the numbers were in a bigger range, and because the algorithm stops at the first hole in the contiguous range of numbers, we don't worry about iterations on a missing range. For example, if the set is 0, 1 to 10,000, we don't worry about iterating from 2 to 10,000, as the algorithm will stop at the first missing number, which is 3. Let's briefly look at the possible implementation. In our code, we don't split the source set, just maintain the max values of the target subsets. Initially, we create the counts unordered map and read the input source into it. So if the source set contains one number x, there will be a pair in the map. Let's illustrate this. For a given source set 0, 1, 2, 4, 8, the map will be as follows. For a source set 1, 1, 2, 4, 8, the map will be as follows because there are 2 1s in the source set. Next, we define the variables m1 and m2 for the max values of both subsets. The values of those variables are set to 0, and we increment both of them as soon as the source subset contains at least 2 m1s. As soon as there was only one occurrence of m1 in the source set, we stop incrementing m2 and keep incrementing only m1. As soon as there are no occurrences of m1 in the source set, we return the answer, which is m1 plus m2. The average complexity of the source code is linear to the number of elements in the source set. The solution is available as a link in the description for this video. Please subscribe if you want to get analysis of other interesting programming problems, and stay tuned.